Next topic, inverse Laplace transforms. So definition of inverse Laplace transform. The inverse Laplace transform is also operation on frequency. So frequency function. So it is denoted by f of s. So that is capital F of s. So the inverse Laplace transform is denoted by L inverse, L power minus inverse. So Laplace transform is denoted by L and inverse Laplace transform is denoted by L inverse. So these two are inverse to each other. So Laplace transform, so we know the formulas of Laplace transform. So we can easily find out the formulas of inverse Laplace transform. So, so that is the inverse Laplace transform is denoted by L inverse. So L inverse of f of s. Some authors may be denoted by f of p in place of s. Some authors in some textbooks, so they are denoted by f of p. So L inverse of f of p is equals to f of t. So that implies, so f of t is equals to L inverse of f of t. So this is basic formula for inverse Laplace transform. Next, so conditions of inverse Laplace transform. So first condition of inverse Laplace transform, L into L inverse is equals to L inverse into L is equals to I. So Laplace transform, inverse Laplace transform is equals to identity element. So that is L into L inverse is equals to L inverse into L is equals to capital I. So that is nothing but it satisfies identity condition. So Laplace transform satisfies identity condition. So next, inverse Laplace transform also linear operations. So that is nothing but inverse Laplace transform satisfies linearity condition. Is clear? In Laplace transform, there is a linearity condition is there. The same here also in inverse Laplace transform. So linear operation. So that is linearity property. So here L inverse of a into f of s plus L inverse of b into g of s plus L inverse of c into h of s. So that implies, so here a is constant. So by using linearity condition, so we can write outside of the inverse property. So a into L inverse of f of s plus b into L inverse of g of s plus c into L inverse of h of x is clear. So this is the linearity condition in Laplace transform, inverse Laplace transform. So once again, L inverse of a into f of s plus L inverse of b into g of s plus L inverse of c into h of s is clear. So by using linearity condition, so we can write the above statement as a into L inverse of f of s plus b into L inverse of g of s plus c into L inverse of h of s. So this is the linearity condition in inverse Laplace transform. So next, so Laplace transform, inverse Laplace transform of piecewise continuous function or sectionally continuous function is clear. So sectionally continuous function or piecewise continuous function. So first example one, in the sectionally continuous function. So find the Laplace transform of f of t. So that is equals to here function is denoted by f of t is denoted by e power t. So whenever t belongs to 0 to 1, open interval t belongs to 0 to 1 and 0 for t greater than or is greater than 0 is nothing but other than 0 to 1 between these interval. So function f of t is equals to e power t 0 less than t less than 1 and so 0 for t greater than 1. So we have to find out Laplace transform of this function. So this is piecewise continuous function or discontinuous function. It's clear? So f of t is continuous on 0 to 1 interval. After that, so 1 greater than t. So f of t is discontinuous function are piecewise continuous function. F of t is equals to e power t 0 less than t less than 1. So 0 if t greater than or is equals to 1. So we can take Laplace transform on both sides. L of f of t is equals to integration 0 to infinite e power minus st f of t into dt. So this is the basic formula for Laplace transform in starting. So this is the basic formula. L of f of t is equals to integration 0 to infinite e power minus st f of t into dt. So this is the basic formula, starting formula of Laplace transform. So here f of t can be splitting into 0 to 1 and so 1 to infinite. So we can split the interval. So integration by parts. In integration by parts, so we can split the integration 0 to 1 and 1 to infinite. So here integration 0 to 1, here integration 0 to 1 e power minus st. So but f of t is equals to in the interval 0 to 1, in the interval 0 to 1, f of t is equals to e power t. So that is integration 0 to 1 e power minus st in place of f of t. So we are taking e power t because within the interval 0 comma 1, so the function value f of t is equals to e power t. So next plus integration 1 to infinite, e power minus st up to 1 to infinite, the f of t value must be 0. So here 0. So within the interval 1 to infinite, the function value, given function value f of t is equals to 0. So it's clear. They can split the integration 0 to 1 and 1 to infinite. In the integration 0 to 1, the function value f of t is equals to e power t within the function value 1 to infinite. Interval within the interval 1 to infinite, the function value f of t is equals to 0. So it's clear. So this second term total 0. So next first term, in this first term, bases are equal, so we can add the powers. So integration 0 to 1 e power t is common. In these two terms, in numerate in powers, t is common, 1 minus s. So 1 minus s into dt. So second term should be 0. So next integrating on integration. So integration of e power x is nothing but e power x. Integration of e power ax. Formula. So integration e power ax is equals to e power ax by a. So this is the formula for integration e power ax is equals to e power ax by a. So this is integration e power ax formula. So we can apply integration e power ax formula on here. So that is integration e power t into 1 minus s by. So here constant is nothing but 1 minus s. That is a. So 1 minus s. Limits are 0 to 1. So we can substitute the limits upper limit minus lower limit. So denominator should be 1 minus s. L of f of t is equals to e power. So in place of t, upper limit. So 1 into 1 minus s minus. So lower limit. Lower limit should be 0. So 0 into 1 minus s. So second term e power 0. So e power 0 is always 1. So 1 by 1 minus s. So 1 by 1 minus s is constant. E power 1 minus s minus e power 0 is always 1. So that is minus 1. So 1 by 1 minus s into e power minus, here minus is common, s minus 1 minus 1. So this is called piecewise continuous function. So Laplace transform of piecewise continuous function or sectionally continuous function. Okay. Next. Some examples are there. So find the inverse Laplace transform of the following functions. So first one, f of s is equals to 1 by s plus 2 by s square minus 3s by s square plus 4 plus 4 by s square plus 16. So we are taking L inverse on both sides. L inverse of f of s is equals to, so L inverse of total term, that is 1 by s plus 2 by s square minus 3s by s square plus 4 plus 4 by s square plus 16. Is clear? So taking inverse Laplace transform on both sides of given function. So that is L inverse of f of s is equals to L inverse of this term. So by using linearity condition, here we can apply linearity property. So linearity property, it shows that, so we can separate each and every term inverse Laplace. So that is first term inverse Laplace is L inverse of 1 by s plus L inverse of 2 by s square minus 3 into L inverse of s by s square plus 1 plus L inverse of 4 by s square plus 16. So this is linearity condition. So by using linearity condition, so by using linearity condition, so formula L inverse of 1 by s formula 1. So L inverse of 2 is constant 2. L inverse of 1 by s square. So that is t. Formula L inverse of 1 by s power n is equals to t power n by t power n plus 1 by n plus 1. So this is the formula for L inverse of 1 by s power n. So using this formula, so here we can write L inverse of 2 by s square can be written as, so 2 into t. So 3 is constant 3 L inverse of s by s square plus a square formula. So cos 2t. So similarly here also 4 into sine 2t, 4t. Here 4 is there, 4 is missing. Here 4 also is. 4 into sine 4t. So this is first example. So next second example, f of s is equals to 4 by s power 6 minus 2 by s power 10 plus 2 by s square minus 9 plus 3s by s square plus 2s. So same, here also same question. Find the Laplace transform of following function. So next, here taking L inverse on both sides. L inverse of f of s is equals to L inverse of 4 by s power 6 minus 2 by s power 10 plus 2 by s square minus 9 plus 3s by s square plus 25. So next 4 is common. So separating L inverse on each and every term of inside bracket. L inverse of 4 by, so 6 can be written as 5 plus 1. So that is L inverse of 1 by s power n plus 1 formula. So that is t power n by n factorial. Next, L inverse of 2 by 9 plus 1. So 2 is common. L inverse of 1 by s square minus. So 9 can be written as 3 square plus 3 into L inverse of s by s square plus 5 square. So that is L inverse of, here direct formula. So this is no need. So we can apply direct formula. L inverse of 1 by s power n plus 1 is equals to t power n by n factorial. Is clear? T power n by n factorial. Here n is equals to 5. L inverse of 1 by s power 5 plus 1 there here. So n is equals to 1. N is equals to 5. T power 5 by 5 factorial. So 5 factorial is nothing but 120. So numerator is 4 is there. 4 divided by 120 is nothing but 1 by 30 into t power 5. So next, second one also same. So t power 9 by 9 factorial into 2. 2 is constant. T power 9 by 9 factorial plus 2 by 3 sin hat. Here a is equals to 3 plus. So 3 into cos 80. So these are the formulas of inverse Laplace using the formulas of inverse Laplace transform. So this is the second example. Next third example. Find the Laplace transform of f of t into sin at and f of t is equals to t into cos at. So here f of t is equals to t into cos at. So taking L on both sides. L of f of t is equals to L of cos at. So but L of cos at is equals to formula s by s square plus a square. So by using Laplace transform formula s by s square plus a square, LHS L of f of t is equals to f of s. So but f of s is nothing but L of t into f of t is equals to L of t into cos at. So this is nothing but so multiplication by t in Laplace transform multiplication by t formula minus d by ds of f of s. So here f of s is nothing but from equation 1 s by s square plus a square. So differentiate with respect to s u by v method. Here u by v method. So differentiation of u by v formula v square u v dash v u dash minus v dash u. The differentiation of u by v formula. So we can apply on here s by s square plus a square. So denominator whole square, s square plus a square whole square. So next denominator should be constant on numerator s square plus a square into 1. S differentiation 1 minus s is constant and s square plus a square differentiation is s square differentiation 2s, a square differentiation is 0. So this is the differentiation of s by s square plus a square by using u by v method. So next simplify s square plus a square minus 2s square. So that is a square minus s square by s square plus a square whole square. So finally s square minus a square by s square plus a square whole square is the answer. So t into cos 80. Laplace transform of t into cos 80. So similarly we can find out t into cos 8 sin 80 also. Next, find the Laplace transform of f of t is equals to t into e power iat. E power iat. Here also same. So Laplace transform of t is equals to 1 by s square. So here. So this is multiplication of t. Laplace transform of multiplication by t. Here formula is there. L of t into e power at is equals to 1 by s minus a into f of t minus a. So 1 by s minus a whole square. So expansion a minus b whole square, a square minus b square minus 2ab. So next rationalize on denominator. So multiply and divided by multiply and divided by s square minus a square plus 2ais. So numerator also s square minus a square plus 2ias. So rationalize here denominator a plus b into a minus b, a square minus b square in denominator. Simplify. So here a minus b whole square expansion s power 4 plus a power 4 minus 2a square s square plus 4a square s square. So numerator is same. Here s square minus a square by s square plus a square. So separating a real part and imaginary part. So e power iat is nothing but cos at plus I into sin at. Ella t into cos at plus I into sin at LHS. E power iat expansion. So RHS, so we can split into real parts and imaginary parts. So therefore Ella t into cos at plus I into L of t sin at. So by using linearity condition on LHS, so by using linearity property on LHS, so L of t into cos at plus I into L of sin at. So that is equals to, so RH is also expansion. So we can separate real part and imaginary part. So separating denominator for each and every term of numerator. So first term s square minus a square by s square plus a square whole square plus I into 2as by s square plus a square whole square. So this is real part plus I into imaginary part. So comparing both real and imaginary parts of the above equation. So we are getting L of t into cos at is equals to previous solution s square minus a square by s square plus a square whole square. So this is the t into cos at formula. So multiplication by t. Multiplication by t of cos theta, cos at. Here multiplication of t of sin at. L of t into sin at is equals to 2as by s square plus a square whole square. So these are the formulas for multiplication of t, sine and cosine. Next, first shifting theorem problems. So first shifting theorem, find L inverse of f of s that is equals to 1 by s plus 2 whole square. So taking L inverse on both sides. L inverse of f of s is equals to L inverse of 1 by s plus 2 whole square. So taking L inverse of both sides of given function. So that is L inverse of f of s is equals to L inverse of 1 by s plus 2 whole square. So here by using first shifting theorem or first translation theorem. So first translation theorem or first shifting theorem. So that is here s plus a. S plus a is there. So in place of a, 2 is there. So that is e power minus at. E power minus in place of a is t is there. E power minus 2t into L inverse of. So we can replace s plus 2 is equals to s. So we can replace s plus 2 is equals to s after applying first shifting theorem or first translation theorem. So that is e power minus 2t is equals 2t into L inverse of 1 by s square. So that is e power minus 2t. So L inverse of 1 by s square is nothing but t. Formula L inverse of 1 by s power n plus 1 is equals to t power n by n factorial. So this one. L inverse of 1 by s power n plus 1. So formula is equals to t power n by n factorial. So this is the formula for inverse Laplace transform. L inverse of 1 by s power n plus 1 is equals to t power n by n factorial. So using this formula here, uh, here L inverse of 1 by s square is equals to t power 1 by 1 factorial, that is t. So final answer e power minus 2t into t. So rechecking the answer. L of t into e power 2t. So multiplication by using multiplication by t. Multiplication of t. L of t is equals to 1 by s square. L of t into e power minus 2t. So by using first shifting theorem, f of s plus 2. So that is f of in place of s is nothing but s plus 2 whole square. So the result is verified. Next, the next example, L inverse of 1 by s square plus 2s plus 5. So find the L inverse of 1 by s square plus 2s plus 5. So here, so 4 can be 5 can be written as 4 plus 1 no? F of s is equals to 1 by s square plus 2s plus 5. So 2s plus 5 can be written as 4 plus 1. So that is 1 plus 4. So first three terms s square plus 2s plus 1. So s square plus 2s plus 1 can be written as s plus 1 whole square. So s plus 1 whole square, s plus 1 whole square plus here. So this can be written as s square plus 2s plus 1. So s square plus 2s plus 1 can be written as s plus 1 whole square. So that is a square plus 2ab plus b square. So that is s plus 1 whole square plus, so 4 can be written as 2 square, 2 square. So we can apply first shifting theorem. First shifting theorem. So we can apply e power minus t. E power minus t L inverse of 1 by s square plus 2 square. S square plus 2 square. So that is formula 1 by a into sine 80. So 1 by a is nothing but here 2 is there. So 1 by 2 e power minus t into sine 2t. E power minus t into sine 2t. So this is the uh, final answer. 1 by 2 e power minus t into sine 2t. So this is 1 by 2 e power minus t into sine t. So this is the final answer for L inverse of 1 by s square plus 2s plus 5. The next example, L inverse of s minus 3 by s square minus, so this is 6s, not 9, 6s plus 13. So this can be written as L inverse of taking L inverse of s minus 3 by s square minus 6s plus 9 plus 4. So 13 can be written as 9 plus 4. So why because written is nothing but so in our current net. So first three terms we can uh, split into, so we can write into a plus b whole square. So that's why we can split the 13 to 9 plus 4. S square minus 6s plus 9 plus 4. So numerator s minus 3. So denominator also s minus 3 whole square plus 2 square. Is clear? So we can apply first shifting theorem or first translation theorem. So e power 3t. So e power 3t. So we can replace s minus 3 is equals to s. L inverse of s by s square plus 2 square. Is clear? So this is after applying first shifting theorem, e power 3t L inverse of s by s square plus 2 square. So this is direct formula. This is direct formula. L inverse of s by s square plus t square is nothing but cos 2t, cos 80. So that is e power 3t into cos 80. So this is direct to Laplace inverse Laplace transform formula. L inverse of s by s square plus a square. So that is here 2 is there. So cos 2t. In case denominator is minus is there, L inverse of s by s square minus a square. In this case, so we are getting cos h80 hyperbolic function. Here cos h80 in case if the denominator contains s square minus a square. So in this case, we are getting cos h80. So find L inverse of s square plus s minus 2 by, so denominator s into s plus 3 into s minus 2. So taking, so let f of s is equals to s square plus s minus 2 by s into s plus 2, s plus 3 into s minus 2. So taking L inverse on both sides. So but here, so we can splitting into this one is nothing but partial fractions. A by S, first term, partial fractions, plus B by S plus 3, plus C by S minus 2. So taking LCM on RHS, S into S plus 3, S minus 2. So A into S plus 3 into S minus 2, plus B into S minus 2, plus C into S plus 3. After LCM, so denominator should be cancelled. Here denominator should be cancelled. So using partial fractions. So next we have to find out here A, B, C values. So how to find out A, B, C values is nothing but, so we can substitute roots of the denominator. So S is equals to 0 is first root. S is equals to 0 is first root, and S is equals to minus 2 is second root. S is equals to 2 is third root. So, so or we can compare the coefficients of s square, s and constant. In this case also we can getting a, b, c values, or otherwise, so we can substitute roots of the denominator. S is equals 0, s is equals to 2, and s is equals to minus 3. So same, so we are getting directly a, b, c values. So after substitution, here s square, s and constant coefficients. So here constant coefficient minus 2 is equals to minus 6a is equals to 1 by 3. So first two equations. Solving these first two equations, we are getting c value. C is equals to 2 by 5. So similarly, b also. So b is equals to 14 by 15. So a is equals to 1 by 3, b is equals to 4 by 15, c is equals to 2 by 5. So substitute these values, ABC values, here in equation star or equation 1. So replace A is equals to 1 by 3, B is equals to 2 by 5, B is equals to 4 by 15, C is equals to 2 by 5. L inverse of f of t is equals to L inverse of A by S. So that is 1 by 3 into S, 1 by 3 by S plus B by S plus 3. So B is equals to 4 by 15 divided by S plus 3 plus C by S minus 2. So C is nothing but 2 by 5 by S minus 2. So here 1 by 3, 4 by 15, 2 by 5, all are constants. So by using linearity condition of Laplace inverse Laplace transform or Laplace transform 1 by 3 L inverse of 1 by S plus 4 by 15 L inverse of 1 by S plus 3 plus 2 by 5 L inverse of S minus 2. So L inverse of 1 by S is equals to 1. So that is 1 by 3, first one, plus 4 by 15. So here we can apply first shifting theorem or first translation theorem e power minus 3t and L inverse of 1 by S. In next step, L inverse of 1 by S is equals to 1. Next, here also we can apply first shifting theorem 2 by 5 e power minus e power 2t. L inverse of 1 by S. So L inverse of 1 by S is always 1. Here also 1, here also 1, here also 1. So 1 by 3 plus 4 by 15 into e power minus 3t plus 2 by 5 into e power 2t. So this is the final answer. So this is special case. So by using Laplace transforms, by using inverse Laplace transform, by using partial fractions, inverse Laplace transforms by using partial fractions. So this is first example in partial fractions. So so next example. So find L inverse of S by S plus 1 whole square. So f of s is equals to s by s plus 1 whole square. So let f of s is equals to s by s plus 1 whole square. So adding 1 and subtraction 1 in numerator. In numerator s plus 1 minus 1. So separating denominator for each and every term of numerator. First term s plus 1 by s plus 1 whole square. First term denominator minus 1 divided by s plus 1 whole square. So s plus 1, s plus 1 cancel 1 by s plus 1 minus 1 by s plus 1 whole square. So taking L inverse on both sides, L inverse of f of s is equals to L inverse of 1 by s plus 1 minus 1 by s plus 1 whole square. So by using first shifting theorem, e power minus t, L inverse of 1 by s. So next here also e power minus t L inverse of 1 by s square. So L inverse of 1 by s square is nothing but t power 1 by 1 factorial. So that is e power minus t. So t into e power minus t. So f of t is equals to e power minus t is common. So 1 minus t. So this is the Laplace transform of inverse Laplace transform of s by s plus 1 whole square. So next find L inverse of 1 by s plus 1 into s square plus 2s plus 2. So here also we can do partial fractions. So inside bracket 1 by s plus 1 s square plus 2s plus 2. So a by s plus 1. So but here in second term of denominator is of degree 2. So bs plus c. Bs plus c by s square plus 2 plus 2s plus 2. So we cannot split into factors. So that's why we are taking numerator bs plus c. So bs plus c by s square plus 2s plus 2. So next LCM, taking LCM on RHS. So a into s square plus 2s plus 2. plus bs plus c into s plus 1 is equals to 1. So equating the coefficients of s square s and constant terms on both sides. So we are getting so b value, a value, c value. A is equals to 1, b is equals to minus 1, c is equals to minus 1. So substitute on here 1 by s plus 1. A is equals to 1 plus b plus c, bs plus c. So that is b is equals to minus 1, c is equals to minus 1. So minus s minus 1 by s square plus 2s plus 2. So in denominator, so we can write 2 can be written as 1 plus 1. So s plus 1 whole square plus 1. So 1 by s plus 1 plus s minus s plus 1 by s plus 1 whole square plus 1. So next taking L inverse on both sides. So here we can apply first shifting theorem, e power minus t. Here also we can apply first shifting theorem, e power minus t, L inverse of s by s square plus 1 square, e power minus t, e power minus t. So this is directly formula, L inverse of s by s square plus a square is nothing but cos at. So that is cos 1 into t. So that is cos t. E power minus t is common, 1 minus cos t. So this is the second example by using partial fractions. Next, applications to differential equations. So using Laplace transform to find the solution of differential equations, that is first order differential equations, first order or second order linear differential equations. So using Laplace transform method to solve the differential equation, y dash minus y is equals to t. So given that y of 0 is equals to 0. So given differential equation is y dash minus y is equals to t. So y dash is nothing but y dash of t minus y of t is equals to t. So taking Laplace transform on both sides of this equation, so L of y dash minus y is equals to L of t. So we know that L of t formula 1 by s square. L of t is equals to 1 by s square. So by using uh, linearity condition on LHS, L of y dash minus L of y is equals to 1 by s square. So we know that L of y Laplace transform of first derivative L of y dash of t is equals to s into y of s minus y of 0. So this is L of y of t is equals to always y of s. L of f of t is equals to f of s. So here also in place of f, y is there. L of y of t is equals to y of s. S into y of s minus y of 0 minus y of s is equals to L of t is nothing but 1 by s square. So that is 1 by s square. So next, so he is given condition phi of 0 is equals to 0. So that is phi of 0 is nothing but 0. So here 0. So taking y of s common, y of s into s minus 1. After taking common y of s, so remaining term is nothing but s minus 1. So that is equals to 1 by s square. Therefore, y of s is equals to 1 by s square minus 1. So, but y of s is equals to L of y of t. So, L of y of t. So, replace on here. L of y of t is equals to 1 by s square into s minus 1. Taking inverse Laplace transform on both sides, y of t is equals to y of t is equals to L inverse of 1 by s square into s minus 1. So y of t is equals to L inverse of 1 by s square minus 1. Here also same. Inside bracket, by using partial fractions, 1 by s square into s minus 1 is equals to a by s plus b by s square plus c by s minus 1. So here s square repeated. So that's why we are taking a by s plus a by s square plus c by s minus 1. Is clear? So these are the partial fractions. So next, taking LCM on RHS, A into S into S minus 1 plus B into S minus 1 plus C into S square. So after taking LCM, so we can compare the coefficients of S square, S and constant. Or so we can substitute roots of the denominator. So put S is equal to 0, S is equals to 1. So we are getting directly B and C values. So put S is equals to 1. So we are getting C is equals to 1 in this equation. Put S is equals to 1. So we are getting C is equals to 1. Next, same equation. Put S is equals to 0. So we are getting B is equals to minus 1. So next, similarly, we can find out the A value also. So A is equals to minus 1, B is equals to minus 1, C is equals to 1. So substitute A, B, C, D values in this equation. A is equals to minus 1, B is equals to minus 1, C is equals to 1. So that is y of t is equals to L inverse of minus 1 by s minus 1 by s square plus 1 by s minus 1. So next by using linearity condition. So by using linearity condition, so that is separate each and every term L inverse to each and every term. L inverse of 1 by s minus L inverse of 1 by s square plus L inverse of 1 by s minus 1. We know that L inverse of 1 by s is equals to always 1. So that is minus 1. Next, minus L inverse of 1 by s square. So that is t power n by n factorial. So that is t square t plus. So by using first shifting theorem, e power t into L inverse of 1 by S, always 1. Or direct formula is there. E power at is equals to L inverse of 1 by S minus A. So this is the answer of, this is the solution for given differential equation. So this is the solution for given differential equation. Verification, y dash minus y is equals to t. So y dash is nothing but dy by dt minus y is equals to t. So this is linear differential equation of first order. So this is of the form linear differential equation of first order. So solution of the linear differential equation of first order is nothing but, so this is the solution. Y of t into y of t into integrating factor is equals to integration q into integrating factor into dt plus c. So first we have to find out integrating factor. So integrating factor formula e power integration p dt. So first we have to compare the given differential equation with dy by dx plus px p into y is equals to q of x. Here, uh, here is there. So dy by dx plus p into y is equals to q of x. So where p is equals to minus 1. So therefore, integrating factor e power integration p dx. So p is equals to minus 1. So e power minus t is the integrating factor. So substitute on here. So solution of the general solution of the given differential equation y into integrating factor is equals to integration q into integrating factor into dt. So y into integrating factor e power minus t is equals to integration q is nothing but t into e power minus t into dt. So here we can do integration by parts. So that is UV method. So directly e power minus t plus t. So integration by parts. So integration by parts. So minus e power minus t into 1 plus t into plus c. So this is the solution. These two solutions are same. So but here is given condition y of 0 is equals to 0. So substitute this condition. We are getting c is equals to 1. So substitute c value. So we are getting final answer minus 1 minus t into e power t. So this is the final solution. Same here. Solve the differential equation y dash minus y is equals to e power t using Laplace transforms given that y of 0 is equals to 1. So y dash minus y is equals to e power t. So taking Laplace transform on both sides, L of y of t, L of y dash minus y is equals to L of e power t. So L of e power t is nothing but 1 by s minus 1. In RHS, L of e power t is equals to 1 by s minus 1. So formula, first derivative of Laplace transform s into y of s minus y of 0. So y of L of y of t is nothing but y of s. But is given condition y of 0 is equals to 1. So y of 0 is equals to 1. So that is y of s is common. First term and last term, y of s is common. S minus 1 minus 1 is equals to 1 by s minus 1. So y of s into s minus 1 is equals to, so here minus 1 is becomes plus 1 in RHS. 1 by s minus 1 plus 1. Next, taking LCM or directly. So here numerator is there in RHS becomes y of s is equals to y of s is equals to 1 by s minus 1 whole square plus 1 by s minus 1. So the next, applying inverse Laplace transform of this equation. After simplification, so we can apply inverse Laplace transform. L inverse of y of s. So that is y of t. L inverse of y of t is equals to L inverse of 1 by s minus 1 whole square plus 1 by s minus 1. So by using first shifting theorem, e power t into L inverse of 1 by s square plus, here direct formula, e power at is equals to 1 by s minus a. So using this formula, e power t. So y of t is equals to e power t into L inverse of 1 by s square. So 1 by s square formula, L inverse of 1 by s plus 1 is equals to t power n by n factorial. So we can say that directly t plus e power t. E power t is common 1 plus t. So this is the second example in applications to differential equation by using Laplace transforms or Laplace condition. The next examples based on convolution theorem. So convolution theorem, f comma g are two continuous functions. F comma g are two continuous functions. So it is defined by f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. Is clear? F of f comma g are two continuous functions on closed interval I, capital I, integers. Then f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. So that is L of f of t into g of t is equals to L of integration 0 to t f of u into g of t minus u into du. So this is the convolution theorem condition. So this is convolution theorem. If the two functions f comma g are continuous functions on capital I, then L of f of t star g of t is equals to L of integration 0 to t f of u into g of t minus u into du. So this is the condition for convolution theorem. Here, example 3. Same, using applications to differential equation. So in previous two examples are based on first order, first degree. So here, second order, higher order differential equations. How to solve the higher order differential equations? By using Laplace transform. Example 3. Solve the differential equation y double dash minus 4y dash plus 8 pi is equals to e power 2t. And also given initial conditions, y of 0 is equals to 2, y dash of 0 is equals to minus 2. So same here also. So we can take, so this is equation 1. So taking Laplace transform on both sides, L of y double dash of t minus 4 into y dash plus 8 into y is equals to L of e power 2t. L of e power 2t is nothing but 1 by s minus 2. 1 by s minus 2. So RHS L of 1 by s minus 2. So we can apply formula. So Laplace transform of second derivative formula s square into y of s minus s into y of 0 minus y dash of 0. So this is the formula for second derivative of Laplace transform s square into y of s minus s into y of 0 minus y dash of 0 minus 4 into first derivative formula s into y of s minus y of 0 plus 8 into y of s is equals to, so L of e power 2t is equals to 1 by s minus 2. So next in RHS, y of s is common. So first y of s, here y of s is there, here also y of s is there, here also y of s is there. So in these three terms, y of s is common. So y of s common s square minus 4s plus 8. Next remaining terms is given. So y of 0 is equals to condition, y of 0 is equals to 2, y dash of 0 is equals to minus 2. So substitute on here minus 2s plus 4. So here also substitute minus 8 plus 8. So total minus 2s plus 2 plus 4 into s, 4 into 2 is equals to 1 by s minus 2. So simplify y of s into s square minus 4s plus 8, so minus 3s plus 10 is equals to 1 by s minus 2. So y of s into s square minus 4s plus 8 is equals to 1 by s minus 2 is as it is. So here, so this term, minus 2s plus 10. So becomes RHS plus 2. So 2 is common, 2 into s minus 5. So plus 2 into s minus 5. In next step, next LCM. S minus 2 is LCM 1 plus 2s minus 10 into s minus 2. So next, so this term. So total y of s is equals to multiply after multiplication, adding some terms, 2s square plus 14s plus 20 21 divided by s minus 2 into s square minus 4s plus 8. So this is. So next, here also, so we can do partial fractions. 2s square plus 14s plus 21 divided by s minus 2 s square minus 4s plus 8. So partial fractions a by s minus 2 plus bs plus c by s square minus 4s plus 8. So after this, partial fractions. Splitting on partial fractions, a by s minus 2 plus bs plus c by s square minus 4s plus 8. After LCM, a into s square minus 4s plus 8 plus bs plus c into s minus 2. So next, the same here also comparing both sides, s square coefficient, s coefficient and constants. After simplification, after comparing the coefficients and simplification of equations. So we are getting a is equals to 1 by 4, b is equals to 7 by 4, c is equals to minus 19 by 4. First, we can compare the coefficients of s square, s. So this is s square, this is s, and constant terms. So solve these three equations. First equation, second equation, third equation. Solving these three equations, we are getting a, b, c values. So that is a is equals to 1 by 4 and b is equals to 7 by 4 and c is equals to minus 19 by 2. So next, replace on here L inverse of A by S minus 2 plus L inverse of Bs plus C by S square minus 4S plus 8. So substitute A, B, C values on here. A is equals to 1 by 4, B is equals to 7 by 4, C is equals to minus 19 by 2. So these A, B, C are constant terms. So using linearity condition, so we can write outside of the L inverse. So we can write by using linearity condition 1 by 4 e power minus 1 by 4 into 1 by s minus 2. So L inverse of 1 by s minus 2 is nothing but e power 2t plus 7 by 4. So 7 by 4 is constant. L inverse of s by separating denominator for first term and second term. S by s square minus 4s plus 12 plus 8 minus 19 by 2. Second coefficient constant c. L inverse of 1 by s square minus 4s plus 8. So 1 by 4 e power 2t plus 7 by 4 L inverse of. So here in numerator we can add plus 2 minus 2. So we can add plus 2 and minus 2 divided by, here denominator we can write a square s minus 2 whole square, a square plus 2ab plus b square. So that is 4 is there. 4, 8 can be written as 4 plus 4. So 1 4 s square minus 4s plus 4 can be written as s minus 2 whole square plus 2 square. Here also same in denominator. So by using first shifting theorem, 7 by 2, 7 by 4 e power 2t L inverse of s by s square plus 2 square plus minus 19 by 2 e power 2t L inverse e power 2t L inverse of 1 by s square plus a square. So that is 1 by s square plus 2 square. So 1 by 4 e power 2t plus 7 by 4 e power 2t into, so direct formula, this is L inverse of s by s square plus a square. So direct formula cos 80, so that is cos 2t plus 7 by 4 e power 2t into, so this is also direct formula sin 2t minus 13 by 4, 13 by 12, 3 into e power 2t into sin 2t. Therefore, 1 by 4 e power 2t plus 7 by 4 e power 2t into cos 2t minus 3 into e power 2t into sin 2t. So this is the example 1 in second order differential equations by using Laplace transforms. So next second one, example 2, solve the initial value problem or solve the differential equation. To solve the IVP, initial value problem, y square y double dash plus 5 dash minus 6 is equals to 0. So initial conditions are y of 0 is equals to 1 and y dash of 0 is equals to 1 using Laplace transform. So given differential equation y double dash plus 5 dash minus 6y is equals to 0. So taking Laplace transform on both sides. So that is L of y double dash plus y dash minus 6 into y is equals to L of 0. So by using Laplace transform of derivative, second order derivative formula, s square into y of s minus s into y of 0 minus y dash of 0 plus Laplace transform of first derivative s into y of s minus y of 0 minus 6 into y of s is equals to L of 0 is always 0. And also we can apply initial conditions. We can write initial conditions y dash of 0, y of 0. So here 1, 1. So y of s is common. So y of s is common, s square plus s minus 6. So remaining terms, s is there plus 2 is there. So that is equals to s plus 2. So y of s is equals to s plus 2 divided by s square plus s minus 6. So in denominator, fractions is there 2 comma 3. So minus 2 comma plus 2. 2 comma minus 2. So factors y of s is equals to s plus 2 divided by s minus 2 into s plus 3. So factors of denominator. So y of s is equals to, so after this one, so we can write partial fractions. So we can find out partial fractions. S plus 2 by s minus 2 into s plus 3 is equals to a by s minus 2 plus b by s plus 3. So taking LCM, so compare the coefficients of s terms and constants. So we are getting a is equals to 4 by 5 and b is equals to 1 by 5. So substitute on here y of s is equals to a is nothing but 4 by 5, 1 by s minus 2 plus b is equals to 1 by 5 s plus 3. So taking inverse Laplace transform on both sides, L inverse of y of s is equals to 4 by 5 is constant, L inverse of 1 by s minus 2 plus 5 by 1 by 5, L inverse of 1 by s minus 3. So L inverse of y of s is nothing but y of t. So y of t is equals to 4 by 5 e power 2t plus 1 by 5 into e power minus 3t. So this is the second one answer by using Laplace transform to find the solution of initial value problems. So next, Z transforms. Find the inverse of Z transform of f of z. So f of z is nothing but z into z minus 1 by z plus 1, z plus 2 using partial fractions method. You know, so find the z transform. So previous are Laplace transforms. So these are the example 6 is z transforms. So z into z minus 1 by z plus 1 into z plus 2. So f of z is equals to z into z minus 1 by z plus 2 into z minus 1. So we can write partial fractions a by z plus 1 plus b by z plus 2. a by z plus 1 plus b by z plus 2. So taking LCM, z into z minus 1 is equals to a into z plus 2 plus b into z plus 1. So next substitute z is equals to 1. So that is nothing but roots of the denominator. First one root of the denominator minus 1. Second root of the denominator is minus 2. So substitute roots of the denominator in this equation. We are getting a and b values. So that is a is equals to 2, b is equals to minus 6. A is equals to b is equals to minus 6. So therefore f of z is equals to 2 by z plus 1 minus 6 by z minus 2. So inverse Z transform. So taking Laplace transform on both sides, L inverse of f of z is equals to L inverse of 2 by z plus 1 plus minus L inverse of minus 6 by z plus 2. 2 is constant. So 1 by z plus 1 formula e power minus t minus 6 constant e power minus 2t. Okay? So this is the Z transform. So convolution theorem. So this is very, very important theorem, convolution theorem. Based on theorem, so applications of theorem is very important. So convolution theorem. So let f of t into g of t are two functions. F of t and g of t are two continuous functions, and L of f of t is equals to f of s, and L of g of t is equals to g of s. Then f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. So to prove this theorem, so L of f of t star g of t is equals to f of s into g of s. So we know that f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. So this is convolution property. So this is convolution property. So this is theorem. So let f of let L of f of t is equals to f of s and L of g of t is equals to g of s. Then L inverse of f of s into g of s is equals to f of t star g of t. Okay. So we know that f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. So these are equation 1 and equation 2. So taking LHS is given LHS. So this is L inverse of f of s into g of s. L inverse of f of s into g of s is equals to f of t star g of t. RHS of equation 1. L inverse of f of t star g of t is equals to integration 0 to t e power minus st f of t star g of t into dt. So this is based on Laplace transform basic definition. So basic definition of Laplace transform. So integration 0 to infinite e power minus st f of t star g of t into dt. So integration 0 to infinite, 0 to infinite e power minus st. So, but we know that from equation 1, f of t star g of t is equals to from equation 2, integration 0 to t f of u into g of t minus u into du. Clear? So, change the order of integration 0 to infinite, 0 to t e power minus st f of u into g of t minus u into du into dt. Next step, so that is change the order of integration, change the order of integration. So integration 0 to infinite, integration t to u to infinite, e power minus st f of u into g of t minus u into dt into du. So in previous du into dt, so we are changing the order of integration d2 to dt. So solve this equation by using substitution method. Put t minus u inside bracket. T minus u is equals to v. T is equals to u plus v. So differentiate on both sides. Dt is equals to 0 plus dv. So that is dt is equals to dv. So substitute on here 0 to infinite, u to infinite, e power s into u plus v. Here u plus v, f of u, g of v into dv into dt. Splitting e power minus s into u, e power minus s into v, f of u, g of v, du into dv. So that is equals to integration u to u is equal 0 to infinite, e power minus su, f of u into du into integration v2, v is equal 0 to infinite, e power minus sp, g of p into dv. So this is from is given question f of u, this is f of u, so this is g of u. LHS is equals RHS. So this is convolution theorem. So once again, theorem statement: f of t and g of t are two functions, and L of f of t is equals to f of s, and L of g of t is equals to g of s. Then f of t star g of t is equals to integration 0 to t f of u into g of t minus u into du. So this is convolution statement. So let L of f of t is equals to f of s, and L of g of t is equals to g of s. Then L inverse of f of s into g of s is equals to f of t star g of t, or integration 0 to t f of u into g of t minus u into du. So this is the convolution theorem statement. In next class, so we can discuss the problems on convolution theorem. So one example is there. L of t into e power minus 4t sine 2t. Solve this Laplace transform. So we know that L of sine 3t is equals to a by a square plus s square. So that is 3 by s square plus 9. That is equals to f of s. Using first shifting theorem, L of e power minus 4t into sine 3t is equals to f of s plus 4. So in place of s, so we can write s plus 4. So 3 by s plus 4 whole square plus 9. So next, so multiplication by t. L of t into e power minus 4t sine 3t is equals to differentiation of this term minus d by ds of 3 by s plus 4 whole square plus 9. So this is integration. So in differentiation of 1 by x form. So minus 1 by x square. So in place of x, s plus 4 whole square is there. So that is 2 into s plus 4 differentiation right into denominator. So differentiation of 1 by x is minus 1 by x square. So in place of x, s plus 2 whole square plus 9 is there. So again differentiation 2 into s plus 4. So this is the final answer. Up to here, our total inverse Laplace transform is completed. In next class, so we can deal with another chapter